Let's begin talking about the properties of aryl halides. Aryl halides, as we were discussing, they show two kinds of properties. Mainly, as expected, they'll be showing nucleophilic substitution reactions. They'll be showing electrophilic substitution reactions as well, because they contain a benzene ring, and this aromatic ring will give rise to the usual properties like nitration, halogenation, sulfonation, etc. But as we were talking and will continue talking, that their properties, electrophilic as well as nucleophilic, they are not very rapid, or you can say that aryl halides are not particularly reactive molecules. They do not show a tendency to show nucleophilic reactions eagerly, as well as electrophilic substitution is also slower in their case. We would try to find the reasons behind this. First of all, let me focus on to nucleophilic substitution reactions. Let's first talk about the electrophilic substitution, nucleophilic substitution reactions which they exhibit. If you remember, alkyl halides, I told you they are very reactive towards nucleophilic substitution reactions, and there were so many of the nucleophilic substitution reactions which alkyl halides they showed. Name a few: replacement by hydroxyl group, replacement by OR group, or maybe NH2 group, maybe cyano group, and we discussed that almost with every kind of nucleophile they gave you a product. In the case of aryl halides, however, the reactions are only a few which are shown, and that too under very drastic conditions. You'll come to know about these conditions, about this contrast with alkyl halides, when you try to follow a few reactions. I'll be taking here the example of chlorobenzene, which is a typical aryl halide here, and when you treat it with NaOH, just like you did in the case of alkyl halides, in their case it was simple treatment with aqueous NaOH or maybe KOH, and it yielded you an alcohol. In this case, what you expect is that instead of Cl, you should obtain OH group here, that is, you should obtain a phenol from chlorobenzene. Now the conditions here become so drastic that you have to heat the reaction mixture to up to 623 Kelvin, and you have to apply high pressure along with treatment with NaOH so as to obtain only a poor yield of phenol here, so that we do not prepare a phenol by this method at all, which shows you the unease of chlorobenzene regarding this kind of nucleophilic substitution reaction, although OH is quite a strong nucleophile. In the second reaction, which I have shown here, is the replacement of this Cl group with NH2 group, and this NH2 group can be obtained here instead of Cl. When I treat chlorobenzene with aqueous ammonia, I have to use Cu2O, copper oxide, as the catalyst here in this reaction, and this catalyst will still be requiring high pressure and high temperature of 473 Kelvin, so as to give me NH2 group here instead of Cl. That is a kind of nucleophilic replacement of this Cl group by this nucleophile NH2. Now, have you seen this reaction? And if you remember the case of alkyl halide, simple treatment with ammonia yielded amines. Here I obtain aniline with such a great difficulty. I can substitute this reagent by potassium amide, which is a very strong base, potassium amide in the presence of liquid ammonia, and I'll be obtaining aniline from here. In this case also the conditions are very drastic. So what I mean to convey to you is that nucleophilic substitution reaction in aryl halides, they are quite difficult to achieve. There is another example in this series. There is another nucleophilic substitution reaction here which I want to show. that is the replacement of this with cyano group. So I have got here bromobenzene and I treat it with copper cyanide. Temperature I have to use is 473 Kelvin, and in the presence of pyridine as a base, I obtain cyanobenzene here. This particular reaction again shows you that even with a strong nucleophile such as cyanide ion, Cn negative, I have to heat the reaction mixture to a very high temperature so as to obtain the substituted product, which makes it amply clear to you that the nucleophilic substitution reactions here, they are not as favored as in the case of alkyl halides, and we'll be finding the reasons for that a little bit later. But first of all, let me tell you that we can increase the rate of nucleophilic substitution reactions with aryl halides, or we may decrease it further by putting certain substituents onto aryl halides. Now, what are those substituents? I am talking about that situation in which I am not going to take plain chlorobenzene but a substituted chlorobenzene here, for example, and that substituent, is it going to have an effect on the reactivity towards nucleophilic substitution reaction? Of course, yes, and that effect is very strong here, depending upon whether the group is electron withdrawing or electron releasing. The rate of reaction can be increased to a great degree or it can be decreased. So it is, the substituents, they have got a strong effect. Now, electron withdrawing substituents, they increase the reactivity towards nucleophilic substitution reactions. And one more point to be noted is that this reactivity is increased particularly greatly when they are present on ortho and para positions. What are electron withdrawing groups, by the way? You remember them as nitro group, or maybe carbonyl group, or maybe this cyano group, which are very strongly electron withdrawing, and if they are present at ortho and para positions, then they increase the reactivity to a great extent. You can take the example, this example illustrates it very well. If I take chlorobenzene and react it with NaOH, I had earlier seen the reaction conditions. Now I am replacing this chlorobenzene with para-nitrochlorobenzene, that is one nitro group is present with respect to para position, with respect to chlorine at the para position, and I obtain the product here as para-nitrophenol, that is chlorine has been nucleophilically substituted by this OH group. I'll be using now only 15% aqueous NaOH, and the temperature is reduced to 423 Kelvin. So earlier it was higher. That means that the presence of nitro group has eased up the reaction conditions. Another illustration in this regard, that if I increase the number of electron withdrawing substituents, then the reaction conditions, they become further easier. Say for example, now I have taken two nitro groups which are present at position number 2 and 4 respectively with respect to chlorine. I now have to use only aqueous sodium carbonate at only 403 Kelvin, and I'll be obtaining the product, substituted product. Similarly, if I use this molecule in which 3 nitro groups are present at 2, 4 and 6 positions, so I've increased the electron withdrawing groups to number 3. 3 number of groups are there. I have to use only warm water and I'll be obtaining picric acid. Picric acid, you know, this is 2,4,6 trinitrophenol, that is Cl has been substituted by OH, which goes on to show that the nucleophilic substitution reaction will become much easier if electron withdrawing substituents are present onto the aryl halides. Similarly, if I talk about electron releasing substituents, what are these? These are, say, NH2 group or OH group, etc. They are having an opposite effect on the reaction and they are the deactivating groups. They'll be having naturally an opposite effect, and if electron withdrawing substituents are the ring activating groups, here these are ring deactivating groups, and they'll be decreasing the reactivity of aryl halides towards nucleophilic substitution. Obviously, when we study about the cause of this lesser reactivity of the substituents, then we will be discussing why is it so with electron releasing and electron withdrawing substituents, and I'll continue with that maybe day after tomorrow. In the meantime, any problems you want to share with me, you are welcome.